agonists. Sorry if I said antagonists. By the way, what's an agonist? Stimulates, right? We've gone through this, I think, before. Did I say antagonist by mistake? What's an antagonist?
Goes against, or like
Right, so it's something that gives the opposite effect or blocks the receptor entirely. Okay? So it could simply stand in the way of the receptor being bound by the natural ligand, right? Or it could actually work in the opposite direction. So alpha-1 agonists are going to constrict arterioles, and what else? Veins. Okay? Both of which are going to do what to your blood pressure? Increase. What's a beta agonist going to do?
Stimulate heart rate. And
Stimulate your heart rate. What does that do for you?
increases how much it
Increases, yeah, good. Increases cardiac output, right? Which will raise mean arterial pressure. Okay. It would also stimulate contraction, right, of the heart, contractility, greater stroke volume, and also more cardiac output. Okay. What would the beta agonist do?
they're gonna dilate.
Yeah, it's going to dilate skeletal muscle arterioles, right? And your blood pressure is going to go even lower, right? So bad. Okay, we're good. So the veins, we'll talk about numbers in a moment. When the blood comes out of capillaries, the venous pressure at those venules is about 15 millimeters of mercury. And then right atrium, it goes down to about 2. Okay, so these are very low pressure vessels. The blood's under very little pressure. And so the blood actually needs assistance in some cases to find its way back to the heart. So if you think 15 millimeters mercury to 2, that's not a very strong gradient, right? So that's a small delta P, which tells you that the rate of flow, right, liters per minute, is going to be very small. So in order to encourage flow, we have a couple of mechanisms. One is the skeletal muscle pump, which you see on the left here. And this is illustrating the fact that when muscles contract in our extremities, particularly our legs, they create pressure on veins locally. Okay? So we have little valves. You could see there's a valve at the bottom, there's a valve at the top. And so when that skeletal muscle contracts, that little segment of blood between the valves, from here to here, we're going to squeeze on that vessel from outside, and we're going to increase its blood pressure. Okay? And so when we increase the pressure here, blood is going to try to go up, and it's going to try to go down. Okay? What keeps it from going down? Valves. Okay? And then the pressure drives the blood the only way it can go, which is out, up. Okay? So this helps us, so if we're just walking along with every step, we have contraction of muscles, and that provides a temporary boost to the venous pressure locally, right? But then we've elevated a column of blood, right? So that little column of blood between the lines is going to get moved up, right? So now we're going to have more volume in the next segment, which stretches the veins out a little bit, right, and elevates the pressure. So we can help this blood move against gravity by walking. The other way is through respiration. When we ventilate our lungs, you might recall that you create a negative pressure in your thorax, right? So if you inhale, diaphragm drops down, right? And if you're inhaling strongly, your thoracic cage expands, right? So all these changes to the volume of the thorax will make the pressure inside low. Okay. And what does that do? Well, all these little arrows are showing you here is that blood is drawn towards that lower pressure, right? So we're reducing the pressure close to the heart when we inhale, right? Inhaling, especially if we inhale strongly, we are drawing blood towards our heart. Okay. So this is going to be kind of a small effect when we're breathing in a relaxed manner, but if we're out exercising, this helps a lot. Okay. So So, if we take all of these things together, we've got a venous system is about 15 millimeters of mercury coming from capillaries. Goes over to about 2 millimeters when we get to the right atrium. Okay, so we've got a pretty small gradient. And we can alter the compliance and therefore the pressure by altering blood volume. Okay, more volume means we're stretching those vessels more, right, and creating more pressure. And the other way is through alpha-1 stimulation through the sympathetic nervous system. Okay, where the skeletal muscle and the respiratory pump fit in is that the skeletal muscles, when they contract, they're pushing on the outside of these vessels, and they're adding to the pressure on those smaller veins that are far away from your heart. Okay, so 15 might temporarily get boosted up to 20. Okay, temporarily. And then the respiratory pump works close to your heart, and it lowers pressure around those vessels, right? So in effect, helping to stretch those vessels out, right? So that that 2 might become 1 or 0 or even negative if you inhale strongly, okay? So what that does is that it tips the gradient a little bit, right? So we can elevate the left-hand side and we can lower the right-hand side and help create a stronger gradient through physical activity. Gravity plays a little bit of a role above your heart, right? Vessels, the veins are going to be, the venous blood is going to be aided by gravity, and it's going to be opposed below the heart if you're standing. Right? But these are the general forces that are involved. Okay. So pretty low pressures. Yeah, question. If I'm upside down too long, can my arteries do what? Yeah, so there's no trouble on the arterial end. So if you're upside down relative to gravity, you can very adequately pump blood to the tips of your toes. Not a problem. The problem you'll have is returning blood from your head, right? So the blood from your head going up to your heart, if you're upside down, is going to be problematic. We don't have valves in much of our heads, and in fact, most of the area above our heart, when we stand normally, does not have any venous valves. Okay, so that blood's going to have a big problem getting back. Okay, so if you do this, stand on your head. I won't demonstrate because it's very uncomfortable. Your head will feel like it's filling with blood, right? And it is. And we sort of rely on the ability of gravity to pull that venous blood down. But in terms of getting blood there, not really a problem. We're dealing with some pretty strong pressures in the arterial system. Okay, so capillaries. What do we need capillaries for? Yeah, this is sort of these are the vessels for exchange. What are we exchanging? Gases, right? Carbon dioxide, oxygen, what else? Sugar and other nutrients, things the cells are using to for energy or for building themselves, right? So nutrients are going from blood into the cells. What else? What else exchanges here? Sorry. Interstitial fluid. Yeah, there's a little bit of loss of fluid in capillaries. We'll talk about that. It's a big part of what we're going to talk about. What else? Is there anything going into the capillaries from that interstitial fluid? Yeah, metabolic waste products. Okay, so carbon dioxide would be one of them. That's one of the gases, but we have some nitrogenous compounds, ammonia, and other things that are produced by cells as waste that go into, right? We have hormones, right? At an endocrine organ, hormones are going into capillaries, and at their targets, they're going to have to leave the capillaries, right? So this is a big big area for exchange throughout the body. There's two ways that this there's several ways that this happens. We can lump them into everything you see here, and then something called bulk flow. Okay, so everything you see here, what is it? Well, we've got diffusion, right? This is a major way that things move, and so we're looking at the inside of a capillary as the red here, as blood plasma, right? And things can go either through cells, right, if they can pass through the cell membrane, right? So what type of substances can pass through cell membranes? Brings you back to the lipid-soluble things, small gases, right? No problem. That's what you see up there in yellow. Some things can fit between these little gaps between cells. Okay, so ions and capillaries will differ as to how much permeability they have to these things. Proteins generally are not going to pass through little gaps. Okay, and what happens to proteins is that they will get endocytosed on the inside. Okay, so an example of this would be insulin. Okay, so you know insulin's a hormone, right? And if proteins like insulin can't fit through the spaces between cells, how do they get to where they're going? Well, they bind to the cells, and the cells endocytose them, right? And then they spit them out the other side in exocytosis. So we call this transcytosis. Substances are picked up on one side and actively pumped, transported, let's say, to the opposite side of the cell. Okay, so lots of substances are moving here, with the exception of this transcytosis. We're essentially talking about diffusion, right? And all the principles apply that we've talked about before, right? Concentration gradient determines the rate of diffusion, right? Another way we have of moving substances is, let me add one thing here. So as blood is moving through these vessels, we go from arteries to arterioles to capillaries. If we look at the total cross-sectional area, right? If we look at your aorta, right? You could probably get your thumb inside of it. And it's got a pretty small cross-sectional area. And as those vessels get smaller and smaller, there's also more and more of them, right? So what happens is actually the cross-sectional area increases over time. We get to capillaries, which is a huge amount. Okay? So what's happening here is, you can sort of think of this as a traffic analogy again, right? You can suddenly the cars have a lot more paths to go down, right? And they they're pushed along, and what happens is that because there's all this space for the blood to go, the blood actually slows down very substantially as it goes through the capillaries. Okay? And this is something that helps to accelerate, or let me put it differently, helps to facilitate diffusion. So diffusion can be very efficient because the blood is moving slowly. Okay. So diffusion of these substances is happening, and as they get to the capillaries, adequate time takes place. Adequate time is there for the efficient exchange of substances. Okay. Then we get to this idea of bulk flow, and this is a little bit of a hard concept to sort of put all the pieces together. But once you've got it, it'll make sense to you, I promise. Bulk flow, just simply defined, is that some of the fluid component of blood, that is this plasma, is able to leak out of the capillaries. And then on the venous side of that capillary, we're able to reclaim most of that fluid. Yeah.
Professor, I have one question about the cross-section.
Oh, yeah.
Of the capillaries.
Yeah, let me, sorry for rushing ahead without seeing it.
You said that the capillaries, the cross-sectional area increases.
Yeah.
Because of all the little capillaries in the kidney.
Yeah.
But not individually.
But now what?
But like individually, it's small.
Oh, yeah. Individually, they're very, very tight. But we're taking the total. So that the blood has only the aorta, that's the only thing it can pass through, right? So 5 liters per minute has to go through an aorta that big. Right? But then when you consider every capillary throughout your entire body, you have lot more paths for blood to take, right? So it's going to be traveling at a slower speed because it's not being propelled through a single opening. There's lots of openings. And that's important. Again, the reason behind this, why this is important, is that diffusion takes time, right? And we need to make sure that the blood is traveling at a speed that allows for everything to exchange. Okay. Okay. So bulk flow is sort of a complement to this diffusion. That instead of relying only on diffusion, what we do is we actually push some of that fluid out amongst the cells, right? And that's filtration, where fluid is leaving the capillary. And then it comes back and gets sucked back in on the venous side of the capillary. And that's a process that's called, here it's labeled absorption. We'll use the term reabsorption. It's a better term. It's reabsorbed. And so this complements diffusion in the sense that we're not just having fluid flow through the capillary and get exchanged across the wall by diffusion. We're actually putting some of the fluid containing the nutrients and gases out into the interstitial fluid. Okay. And then we reclaim at least most of it. Okay. So 2 processes going on here. There's filtration when we lose substances across the capillary wall, and then reabsorption when we reclaim them. All right, so what kind of things are happening to make this happen? This is going to have a lot of importance, not only here, but when we get to the kidneys as well. Same concepts, and kidneys will be of very soon get there. Believe that? Okay. All right. So here's a little chart showing you the blood pressures, right? We looked at the arterial pressure. It goes up. Let's say this one looks like it's going between, I don't know, like 70 and 110, right? So 110 over 70, right? It's fluctuating up and down. And then as you move along, that pressure change, that pulse pressure gets smaller and smaller, right? And you can see overall that our blood pressure is declining. Okay. And the reason is that at any given point, we've got less and less distance to the end, right? So just conceptually, if you're talking about the pressure here, blood is going to have to pass through all these vessels before it can get to the end, right? So that's a lot of resistance, okay? Which explains why we've got such a high blood pressure. But if we take a point right over here, right, now there's much less resistance in front of it, so its pressure is lower, okay? So it's all that resistance that's providing the source of the pressure. Okay. Well, when we look at the capillaries in particular, right? At the beginning of capillaries, this is just an average, but at the beginning of capillaries, what's our blood pressure? I helped you by drawing red lines. It's 35, and it goes down to 50. Okay. So like any blood vessel, along the course of its length, its pressure is going to drop. Okay? The aorta at the beginning and at the end is a little bit different, right? All these vessels, they're losing pressure as they go. So we have a pressure range here, okay? Specifically, we are talking about pressures that are termed hydrostatic pressures. So if we take a cross-section, of a vessel, hydrostatic pressure is the force applied unidirectionally to the walls of that vessel. Okay? So it's a pressure that's pushing out. This is hydrostatic pressure. Okay? So whenever we talk about blood pressure, we are talking about hydrostatic pressure. It's a fluid pressure. Okay? So we can take our capillary, we make a very simple capillary here, and we can see that at one end it has a pressure, so PC is pressure of the capillary blood. It's 35 millimeters per mercury, we just looked at that. And then on the venous end, it's going to be 15 millimeters of mercury. So it changes, right? No surprise. All vessels change in hydrostatic pressure as you go, it gets smaller. Okay. What is the pressure of the interstitial fluid, IF? 0. What does this mean? If this were positive, we could sort of illustrate this as pushing into the blood, right? How could you make an interstitial fluid positive? Yeah, if there's a buildup of fluid, right, it might be positive. Or if you squeezed your arm externally. So we could apply pressure, but most of the time, interstitial fluid is not going to have pressure. Okay. So we could say that we have a hydrostatic pressure at the capillary and of the interstitial fluid, and we have the same thing on the other side. Okay, so these are hydrostatic pressures. These are the easy ones. So let's talk about the other type of pressure. What's the other type? Osmotic. Okay, so osmotic pressures are going to be moving substances across the capillary wall. Okay. And these are pressures. Remember that little U-shaped tube we looked at? What was that, the second day of class? Osmotic pressures are the result of osmolarity differences, right? Remember that? Okay. So let's see what we're dealing with here. We want to measure this. Physiologists will always use a reference solution, right? What's your standard? Is it hyperosmotic or hypoosmotic compared to what? What's our standard? Yeah. So we have our standard, which is normal saline. This is a term that's used for a saline that is 290 millimoles per liter, right? 0.9% sodium chloride. And sometimes it's given intravenously, right? Normal saline. Okay. This is our standard. So relative to that, we've got blood. Okay. And blood's osmolarity is a little bit different. It's very close, but it's a little bit different. What do we have here in blood? Dissolved in plasma. That's not present in our normal saline. So I have one vote for cells, one for proteins. Both are true, but osmotically the cells don't mature. Okay, they're too big. We might consider cells to be in plasma as a mixture, right? Whereas proteins are in as a solution, okay, part of the solution. So the proteins are there, right? And so we've got proteins there that aren't present in our normal saline. Okay. And relative to our reference solution, we've got a bunch of ions, right? Mostly sodium chloride, proteins and other things as well. Okay. So we have an osmotic pressure, right? So the way that we represent this is with pi C. Okay, so this is the osmotic pressure of capillary blood. Okay. All right, so we can identify those there. What this value is about 28 millimoles per liter. Okay, so that's the osmotic pressure. This is the pressure that's that we can describe due to the plasma, including its proteins. Okay. And if we take our interstitial fluid, we want to know its osmotic pressure. Its osmotic pressure. Well, compared to normal saline, it's not the same. Right? If we take interstitial fluid, it's made up of sodium chloride, right, and some other organic molecules in small amounts by comparison. Okay. It's essentially zero. What those ions are might be a little bit different, but normal saline is called normal saline because it's matched to this interstitial fluid. Okay. So there's no osmotic pressure here. If we want to be accurate, tiny, tiny amounts of proteins, but really not much. Okay, so we put it all together, right? And what are we dealing with? We are dealing with hydrostatic pressures pushing out of the blood. Hydrostatic pressures pushing in, but remember that's not zero. We've got osmotic pressures in both directions, right? The osmotic pressure of the capillary blood is to pull fluid in, right? And then we've got the osmotic pressure of the interstitial fluid pulling out, which is very, very small. We'll use 3. It's 3 because there's a little bit of proteins here that might pull back. Okay. All right, so we've got 4 values. Make sure you got them down. We've got the hydrostatic pressure of the capillary blood. We've got the hydrostatic pressure of the interstitial fluid. And we've got our osmotic pressures. We've got our osmotic pressure of the capillary blood, which is strongly pulling fluid into the blood. Right? And then we've got our osmotic pressure of the interstitial fluid. It's very small. So, if we're going to account for these things, how can we do it? If we want to say, let's just take the arterial end. How do we account for all these 4 different forces? How would we do that? You could have one. Yeah. It's math, people. But this is the friendly kind of math where it's not so bad. So we've got 35. What else do we have? 3. Okay. And then we subtract those that are working in the opposite direction, right? Right? You see where I got that? 35. And 3 are positive, they're pushing the fluid out. Right? Pushing the fluid out. And then we have negative values. 28, 0. Okay. So it's simply, what we're doing conceptually is saying, we have a hydrostatic pressure in capillary blood. And we've got this little interstitial fluid osmolarity, both working in the same direction. We'll add those together. Okay. So together they make up 38. Okay. And then we'll subtract those that are working against it. You see? All right. So if you do this, what do you get? 10. Okay. And if we do the same thing on the other side, we get a value that's about the same. Okay. However, it's a negative value. Okay. So we could say that we have a plus 10 force, right? And this force is a combination of hydrostatic and osmotic. Okay. On the arterial end. And then on the venous end, what is it? It's minus 10. Okay. It's actually a little less than that, but we're okay. Okay. So positive values are fluid leaving. Okay. What do we call that process of fluid leaving? That's filtration. Okay. Negative filtration is reabsorption. Okay. So let me put that in context real quick. Okay. So here we are back at the same slide. We have a filtration where we've got hydrostatic capillary blood pushing out, right? And we've got osmotic interstitial fluid, a little bit of activity working in the same direction, right? Being opposed by the osmotic pressure of the capillary blood, right? All these forces are working together, but we have a net filtration, okay? About plus 10. And fluid is filtered out, okay? So, not only do we have diffusion, we're actively pushing some of that fluid out into the interstitial fluid, okay? And then on the opposite side, we're reabsorbing, right? Because we have a negative pressure. Now, these two values are not exactly the same, as I alluded to, and over the course of a day, there's a difference of about 4 liters. Okay? So that is at every capillary throughout your entire body, working 24 hours a day, we have slightly more, very, very small amount more filtration than we do reabsorption. Okay? So we have a net loss, but we reclaim 75, 80% of it, most of it. Okay. Why do we do this? Why do we do this? This is not an accident. This is on purpose. This helps us. In what way does this help us? Yeah. It allows us to get rid of metabolic waste products, yes. And it allows us to receive nutrients, okay? So you can kind of think of these little arrows up here kind of showing you that we've got cells out here, right? We've got all kinds of cells here. And what's going on is there's like a little microcirculation happening out here in the interstitial fluid. Okay? So those cells are like, think of them as like little rocks in a slow-moving river, right? Everything they're producing is being swept away slowly, okay? And it's being moved towards the blood. But the same can be said for what's coming from upstream, right? We've got glucose and oxygen and all these things moving actively towards our cells. Okay? So we rely on diffusion, yes, but to enhance diffusion's effect over distances, we are able to have this little microcirculation. Okay? But why do we have an excess? What do we do with that extra fluid? We've got 4 liters a day, that's surplus. Where are you gonna put it? That's a lot of fluid to carry around with you, right? But it eventually goes back to the blood, right? How does it do that? Through the lymphatic system, yeah. Okay, we'll talk about that in a moment. All right, so, something weird happened in my slides here. Hang on. Pay no attention. Okay. All right, so I want to see if you can sort of grapple with this idea of these hydrostatic pressures and osmotic pressures. Okay, and a great way to do that is to take our situation, which is represented here as the red line in the middle. Okay, and let's see what happens when we change things. Can you understand why it changes? Okay, so we've got a blood pressure in red here. Just follow me. We've got a mean arterial pressure of about 90 there, and it's declining over distance slowly. We get to the arterioles, right? And arterioles provide a lot of resistance, so once we are moving through these arterioles, we're losing a lot of pressure. Okay, and when we get to our capillaries, the beginning of our capillary, we said it was about 35, right? So right about here, we're at about 35 millimeters of mercury in our capillary. That's the start. And then when we get to the end, we're down around 15. What happens when we constrict our arteriole, right? Or when we dilate our arterioles, what happens? Okay. So if we constrict our arterioles, right, we've got vasoconstriction here in purple, now we are lowering the hydrostatic pressure that arrives, right? Because what we're doing is sort of like a faucet in your house, right? We're closing off the valve to the capillaries, right? And so we get less and less flow into that capillary, so the pressure drops, right? All right, so what is happening here? I don't want you to do any math here, but I want you to conceptualize what's happening under conditions of vasoconstriction and vasodilation, okay? first, we'll take a little bit of time here and we'll talk about vasodilation to start with, okay? So we're gonna vasodilate here and see how much time we have. See if you can explain what's going to happen to the process of reabsorption and filtration at the capillary in our green example here at the top, okay, vasodilation. The question is to answer, what happens to filtration, what happens to reabsorption? What's going to happen to filtration under vasodilation? Yeah.
Will it increase?
Well, he says filtration increases. Why do you think that?
Because there'll be a higher hydrostatic pressure in the capillaries, so it'll cause more fluid to push through.
Okay, we've got a higher hydrostatic pressure in the capillaries. You can see our green line is elevated, right? So the capillaries, at the beginning of the capillary and at the end, we've got higher hydrostatic pressure. And that hydrostatic pressure favors what process? Filtration or reabsorption? Filtration. Okay. So at the beginning of the capillary, we're going to get more filtration than we did before. Okay. What about reabsorption at the end? We'll have less reabsorption, right? Again, because that hydrostatic pressure of the capillary blood is working against reabsorption, right? So reabsorption's the process of pulling that fluid back, right? Which depends on a low hydrostatic pressure. So we said that our hydrostatic pressure of the blood is elevated. Okay. All right. So in a nutshell, we've got more filtration and less reabsorption, right? So what does that mean for bulk flow? We're gonna have more fluid leaving altogether or less?
More.
Yeah, we're gonna have a net loss of fluid from the blood. If you have a local dilation, why would that make sense? Why would that benefit? Yeah, so one of the reasons you might remember is that we have vasodilation is one of those autoregulatory things is these cells are in metabolic need. Okay, so we vasodilate when our cells don't have enough oxygen, right? And so what this does is, yes, it brings more blood overall, but more of that fluid in the blood, including the oxygen, is being brought to those cells. Okay, and then constriction does the opposite, right? If we constrict an arteriole and we have less blood going to that capillary, we have lower pressures, right? And so what happens in our purple example here, right? We have lower filtration and greater reabsorption, right? Yes?
So could you explain why hydrostatic pressure is increasing with vasodilation?
With vasodilation, you are allowing more blood through the capillary, or through the arteriole. Okay? So instead of